Okay, so now we want to talk a little bit about our second group of structures, geologic structures, and that's going to be faults. And so sometimes when we have rocks that break or deform in a brittle fashion, the layers get tilted, we talked about. And so sometimes hiking around, you can see when layers are no longer horizontal, that's an indication that something has occurred here. We said we would have to do some investigation to figure out, was a fold, this is a fold structure, or a fault structure. Now that's not always true when it comes to brittle deformation. And so sometimes the rocks break and the layers remain relatively horizontal. And so instead of looking for a tilt in the layers, we're looking for a place where it has been broken. And so now there's lots of places that rocks have been broken. And so how do we tell the difference between a crack, or what we might call a joint, or a fracture, and a fault? Well, this is where the layers come in again, right? So in this picture here, as you look at this face, there is a feature that runs down here. Kind of do that. It's not super obvious, but it's a crack here, right? Or a fracture. So is it a fault or is it just a fracture? What we're going to do is we're going to use the layers to indicate that there has been motion. And this is the difference between a fissure or fracture and a fault. A fault is a break where there has been movement across that breakage. And so because we know something about our sedimentary rocks, that they're deposited horizontal and they're laterally continuous, which means they go on for a long period. When we look here, I see this layer abruptly stops, this white layer here, and then it's up here across this feature. That's an indication there's been motion, and so I would argue that this is not just a fracture or a fissure, it's a fault. And I can draw a line across that feature that would indicate the fault, or in this case maybe the fault plane, and I can look and say, how has that motion moved? What's happened here? Well, if these layers were once laterally continuous, right, they went through here, and there's been a movement or a shift, and here we would argue that this side of the block must have moved down, or maybe this side has moved up, but there's definitely been some motion that I can indicate across that feature. Right, so this is what happens when we have brittle deformation. And so we want to investigate a little bit about how to tell the difference between different types of motions that we see, because unlike our folds, where we're going to argue that the dominant type of stress that's causing those is compression, for faults, we can have all three of our stresses be applied to the rocks and create a fault. And we want to look at those because they have different properties. We're going to give them different names. Okay? And so there is a convention for how we look at faults and how we name them. And so our first group of faults is what are called dip-slip faults. So what does that mean? It means that there has been some type of vertical motion on my fault, which means the blocks have either moved up or down. And there's two different types of faults that we want to identify. And so just like an anticline and a syncline, we have to look at the properties of the structure and figure out which one we have. And so there is a process to do that. And so we're going to walk through that right now. And so the first thing to do is to identify that, of course, you have a fault. And as we look at the image on the right here, hopefully you could see that there's this crack or fracture, and because the layers no longer line up, it's an indication there's been motion. So I feel pretty confident that this is a fault, and then I can draw a line across that feature and define that as the fault plane. Okay? The next thing I want to do is determine motion. So here's the trouble. Because I never saw this block or this structure or these layers shift, I don't know if under stress this piece of my view here, right, or block, was pushed upward, okay? And so that might have happened. So we added some stress and this block went up. The other possibility, of course, is that when stress was applied, this one didn't move at all, but this one moved down. That is a possibility. The other case might be that this moved up a little bit and that moved down a little bit. And so because I have these three options, it can be confusing if we all just looked at it and you decided to look at the right block and I decided to look at the left block, and then we would have some confusion about what actually happened here. So this is why there's a convention that we use that says, look, we are going to always look at what we're going to call the hanging wall, which is the block that is above the fault plane. So remember, this line is the fault plane. I just drew that. And how do we know it's above? Well, look, there's a bunch of ways you can do it. The easiest way, I would argue, is if you put your pencil or pen on the fault plane and just draw a straight line upward, right, vertical to the top of the page, you will be in the hanging wall. This is the part of the block, right, that I want to look at always to evaluate motion, okay? So what we're going to say is that is the hanging wall, and we define the other block that's been kind of, bisected by this fault plane as the footwall. But the trick is, hanging wall, footwall is important. If you don't remember the names for my class, it is not the end of the world, but I need you to always look at the correct block, which means if you identify the fault plane and you can figure out that I want to look at the block that is always above the fault and tell me which way it went, you can still identify the fault, okay? So, which way did this fault move? I only care about the hanging wall. And so, relative to the other side over here, which way did the hanging wall move? Right? So we can see that the hanging wall moved up relative to the footwall. Okay? And that's how we're all going to evaluate this structure. This is why we say everybody needs to look at the same side of the block and determine which way it went so that we're all on the same page. We can all come to the same conclusion. All right? And so it is true that maybe this went down, but it doesn't matter. Our convention says, look at the hanging wall and tell me which way it goes, and we can use that to figure out what fault we have. So, we said dip-slip faults. There are two of those, okay? Here's an example of a dip-slip fault. There has been vertical offset. So there's been some up and down motion on my fault here. And so what I want to do is figure out which one I have. There are two types of dip slips. One we're going to call a normal fault, and one we're going to call a reverse fault. So what do we do when we see our offset here? Is the first thing we need to do is figure out which block am I going to evaluate. So whether you name them as hanging wall and footwall, to me, is not as important as that you can identify the fault plane, which is right here, put your pencil on the fault plane and draw a line vertical. You are now in the block that I want you to evaluate. This is the hanging wall, but it is the block that you need to evaluate motion. And then you look across and say, how did this layer get here? It used to be here. It must have went down. And so we're going to argue that the motion on this fault is the hanging wall, or this block, moving down. Okay? That indicates a normal fault. Okay, so whenever the block that is above the fault plane moves down, you have what's called a normal fault. That is always going to be true as long as you're looking at the right block. Okay, not the right side, but the correct block, I guess I should say. Okay, so identify the fault plane, go straight up. This is above the fault plane. This is the block I care about. how did it get to here? If, right, these layers were connected, it went down. Moving down is a normal fault. So sometimes for me, visually, when I look at a side view, right, so the way that we can identify these is we need a cross-sectional view, a side view. Without it, I can't figure out what I have. So in a side view, to me, I always think of, if this is the fault plane, this block is kind of resting on this incline, and it is sliding down like the slide in a playground, let's say. You jump on the slide, where do you go? You go down. That's normal. That's what happens when you go on a slide. And so moving down the slide is normal. It kind of helps me remember down is a normal fault, right? The other thing we want to associate with this is that the stress that causes normal faults is tension. We are pulling the crust apart here. So in places on the surface of the earth or on the earth, we have stresses that are trying to stretch the crust of the earth. Now, the earth and the layers close to the surface are colder and tend to be more brittle. So we can't stretch them like taffy. They don't want to deform that way. So this stress actually causes them to break. And pulling apart causes this type of fault to occur, where the blocks slide down. When I evaluate my fault plane and I look at the hanging wall, down the slide means normal, means tensional stresses, and we would argue that we would get a lot of these at places where we're pulling the crust apart. That might be a divergent plate boundary if I had to choose a plate boundary to associate with that. Okay, so look, the other choice you have when you're looking at dip slips, remember dip slip means that there has been some type of vertical motion. We still want to look at the fault plane and identify it. There it is. And we want to say, where's the block that I care about? I put my pencil on the fault plane, and cursor, I guess, because we're online, and go straight up. I am in this block. This is the block I care about. So relative to here, if this used to be connected to this brown layer, where did it go? It went up. So now I have a dip slip fault where the hanging wall or the block above the fault plane went up. It went up the slide on the playground. That's not normal. So we're going to call that a reverse fault. Okay? And so we still have our hanging wall footwalls, but what causes this type of faulting is compressional stresses. When I crush the rocks and they're brittle, they tend to fail in this fashion. And so here I am compressing the rocks like this. And so whenever I try to shorten the crust or compress the crust, I get these types of faults where I have the hanging wall or the block that is above the fault plane moving up. So here's the key. When you're doing a homework or you're doing a quiz and you're given a block diagram or a map view, you have to know that when we're talking about faults, in order to identify a dip slip fault, which means a normal or a reverse, you must be looking at a cross-sectional view. You can't have a map view, because in map view, and you're in your plane looking down on the surface of the earth, you can't tell up and down motion, and you can't tell the orientation of the fault plane. So without that information, you can't identify a dip slip. So the trick here is, if you're given a diagram and it says map view, it can't be a dip slip fault. If you're given a diagram and it says this is a cross-sectional view, then you know it must be a dip slip, and you'll go through this process to figure if it's reverse or if it's normal. Okay? The last thing I'll tell you about the diagrams and homeworks is that if you look at these, remember, just because I've drawn this fault plane in this direction doesn't mean all the diagrams will look that way. I could certainly draw a diagram where the fault plane is tilted this way. But the process would be the same. You want to put your cursor, your finger on the fault plane and go straight up. You'll be in the block you want to evaluate, and you'll evaluate whether it went up or down. If it went down, it's normal. If it went up, it's reverse. The last type of fault that we need to talk about is going to be what's called a strike-slip fault. So here, we need a different view to identify this type of motion. So strike-slip faults are where the rocks are sliding past each other. So no more vertical offset, but a shearing motion, a sliding past motion. What does that mean for you? Well, the good news is there's only one choice here. So if you can identify this fault as a shear stress fault, then you know what you have. It's a strike-slip fault. As opposed to the other one, you have two choices and you have to kind of go through that progression to figure out which one you have. Here, if you know the type of motion, you say, hey, this is a strike-slip, and you're done. How do you know? We need a map view. So this is just the opposite of the dip slips. I can't look at the cross-section because there's no offset, there's no up and down motion. I need a map view. I need to look down on the surface of the earth to see an offset. Then I'll know it's horizontal, and then I'll know it's a strike-slip fault. Okay? So the type of stress for this one is shear stress. So now we've identified our three types of stresses with our three types of faults. Reverse is compression, normal is tension, strike-slip is shear. So you need to be able to associate those with their proper structure. And so the difficult part might be that when we're looking at a map view, we don't really have layers, so we have to use other features. And of course, an example that I can show you is the San Andreas Fault. The system here, in most places, it's a transform or a sliding, right? A shear stress is causing a strike-slip fault here. So what we're using in some places is this river has been cut, or this wash has been offset, has been moved horizontally. You can see a little closer in this example here, right? Streams should just come across and flow downhill. This jog or this change in direction is an indication that the block on the right and the block on the left are moving horizontally. Here's my fault, right? It's the contact between the two blocks. And this feature is telling me offset here, right? So the San Andreas gives me that information. And so this is a strike-slip fault. We're not going to go into the different types. So it's either a normal, reverse, or a strike-slip. If you can tell me it's a strike-slip, you're good. So this is the trick when you're looking at block diagrams. If you're given a block diagram, and this is why I told you it's very important to pay attention to your view. If I say identify this structure, is this a reverse fault, a normal fault, or a strike-slip fault? And I give you a map view. You can't identify a reverse or a normal in map view, so it must be a strike-slip fault. Right? So use your views wisely. Make sure you always check on those and know what you have. That way you can tell whether you have a strike-slip fault or normal or reverse, right? So the views are definitely important. Right, and so this is part of a big transform boundary. Once again, if I had to associate the stress with a particular boundary, a transform boundary would be a good choice. Now, just to point out a few other things that you might run across that might be a little confusing, and that is the term thrust faulting. In your readings and some of the videos, you might hear this term. For us, we're still going to just refer to that as a reverse fault because it is just a reverse fault. It's just a special one, a low angle dip, which means you can see from this diagram the angle of the fault plane is pretty shallow. It's not very steep. Now look, the process of identifying this as a reverse fault that we went through still works. You identify the fault plane, here it is. I put my cursor on it and I go straight up. This is the block that I care about. And I say, how did this layer get here if it used to be connected here? It went up the slide. Going up the slide is not normal. This is a reverse fault. and it is a reverse fault. Right? So for us, we're going to say that reverse faults, thrust faults, same thing for this class. So no one should be confused by that. But that process still works. You call it a reverse fault, and you're all good with that. Okay? So there's the hanging wall and the footwall, right? And then just tidying up a couple terminologies. We talked about dip slip faults. We talked about strike slip faults. In reality, most faults are a combination of both horizontal and vertical offset. Might call that an oblique slip fault. But we're going to say that, look, when the San Andreas Fault ruptures, most of the motion is going to be horizontal. Maybe it moved up 2 inches, but it slid, 10 feet horizontally. So obviously, we're going to argue that it is a horizontally moving fault, it is a strike slip fault. Or if there's a big uplift, right, a dip slip fault where the block moves up, 5 feet, maybe it slid to the right or left horizontally a couple inches, but the dominant motion is horizontal, or is vertical in that case. So we're still going to identify it as a dip slip. Okay, so it's just kind of a reality check that, look, whenever faults occur, they're not perfectly all horizontal or perfectly all vertical. There might be a small component in the other direction. We're looking at the dominant motion to be able to identify what we have. So I don't want you to get kind of confused by terms like that. Just a little bonus slide. So look, we have lots of normal faults here in Arizona, and that is because the southern part of the state is actually being stretched. It's being pulled apart. We said that tension is what's causing normal faults as we stretch the crust. The crust is brittle, and it behaves in a brittle fashion by breaking. And the type of motion we see on those type of dip slip faults is the block above the fault plane goes down the slide. And so this is a much more complicated version of that. But when you look at part of the valley, if you were up at South Mountain, and you look to the northeast, you can still see some of Papago Park there. It's those brown layered kind of buttes that poke out of the ground right across from the zoo. What you're really seeing is the hanging wall of this very low angle fault here, where we're pulling this down the slide, so it's a normal fault. It just so happens that in the process of this faulting, the hanging wall itself also broke, and even the motion on those is also normal as we extend the crust here. And we pull out this kind of metamorphic rock / igneous rock up to the surface that used to be way down here. That's what's exposed at South Mountain. And the little buttes that you're seeing are the remnants of these layers that have been buried by the basin fill. All the mountains, right, the weathering material is being transported off the mountains into the valley and filling up the valley. And it's filled that in with this sediment, covered most of this, but just leaves this little part here. And so if you go to Papago, you can see the beds are tilted. That should be an indication that something's happened here. Is it a fault or a fold? Well, we definitely have to do some more investigation. And this certainly is a little more complicated, but the basics still hold true. A hanging wall, blocks that are above the fault plane that are moving down the slide, makes it a normal fault. And the stress associated with that is tension. Right? So we want to make sure that we can associate the right stress with the right structure. Okay, so I'm hoping that that's enough information to get you through some of the quizzes and assignments that you have for this module. Remember that the lab is also going to cover structural geology, so there's some overlap here, hopefully, and some reinforcement. So make sure you go through those and take your time. Make sure you understand the content. If you're not sure, for sure, make sure you contact me before you take any of the quizzes. The articles and the video all should help reinforce these concepts. Okay? All right. Good luck.